The second video lab report analyzes the motion of a falling object according to the fundamental principle, which is Newton's second law. This presentation on the experiment will cover the following topics: the fundamentals of the experiment, analyzing the experimental data with Tracker, creating computational models of the experiment with VPython, comparing the expected position with modeled positions as a function of time, and last, answering the what if and what does it mean questions. In order to describe the fundamentals of this experiment, one must first begin with a fundamental physics principle. Here, we begin with Newton's second law, where, as it is shown, Vf is equal to Vi plus Fnet divided by m times delta t. In this experiment, the object's velocity is not changing and is therefore accelerating. As a result, Fnet is not equal to 0 in this scenario. Instead, Fnet is initially equal to the weight force W, which considers the mass of the falling object, Earth's gravitational force, and a unit vector, j hat. The VPython code shown here displays these relationships. The experiment, which I ran, included dropping a Wilson TDS football and letting it fall to the ground as it accelerates. The system here is the football with a mass of 0.415 kilograms. The surroundings include the environment and all field forces which act on the falling football. It should be noted that in the experiment, the football fell negative 1.562 meters during a 0.581 second time interval. After the experiment was run considering only the effect of gravity, one had to consider the drag force acting on the falling object as well. As a result, Fnet is now equal to W plus Fd, where Fd represents the drag force acting in the direction opposite of motion. The VPython code shown here again displays these relationships. As you can see from the physical experiment, the football is dropped from my roommate's hand and falls to the ground. It falls right along the oriented y-axis for 0.581 seconds and travels 1.52 meters in the negative y direction in this video clip. The graph on the right shows the correlation between position in the negative y direction and elapsed time. Note that this relationship is not linear because the football is accelerating as it falls to the ground. As was previously mentioned, the experiment was first analyzed using only the weight force as a determinant of Fnet. This is shown by the VPython code where Fnet is equal to W. The code also shows that W is equal to the opposite of the football's mass multiplied by little g, which is 9.8 meters per second squared, and the unit vector j hat of 0, 1, 0. The results are shown by the computational model which, when run, shows the force of gravity acting on the falling football. The experiment was analyzed a second time, this time considering the drag force in addition to the downward force of gravity. This is shown here by the VPython code where Fnet is equal to W plus Fd, where, as it was mentioned before, Fd is the drag force which acts in the opposite direction of motion. The value of this unit vector was selected by taking approximately half of the magnitude of the drag force constant b and using this value as the y component of the unit vector. The aeroscale value was determined by dividing the distance which the ball traveled, 1.562 meters, by the weight force of the falling football. This aeroscale was then applied to both the weight force and drag force as shown in the code, which provides arrows which then represent the respective forces acting on the system. The chart displays the three cases which were considered during the experiment. The orange dots represent the actual position of the football as it falls to the ground during the 0.581 second interval. The solid red line represents the predicted position of the football as it falls when only the weight force was considered. Alternatively, the solid blue line represents the predicted position of the football as it falls when both the weight force and drag force are considered. It is interesting to note that according to the model including only gravity's force, the ball falls further than the model considering the drag force in addition to the weight force. This is logical because the drag force would slow the ball down and as a result it would not travel as far during the same time interval. Both models underpredict the position of the football initially, but it should be noted the model accounting for drag matches the final position of the actual experiment. Overall, the model which accounts for drag and the force of gravity fits the actual data better than the model which accounts for only the force of gravity. The definition of the change in velocity is that delta v is equal to the change in position over the change in time of the object in motion. And in this particular experiment, the slope of the experimental position versus model position chart is equal to velocity because the chart plots the change in position of the football as a change in time. As I noted, the slope of the red line, the model which accounts for solely the force of gravity, has a steeper slope indicating that the velocity is still changing as time progresses. On the other hand, the blue line, the model which considers the drag force as well as the force of gravity, has a flatter slope, indicating that the velocity isn't changing greatly as time elapses. This means that the object has reached terminal velocity, the point at which it doesn't accelerate any further. This is represented by the set of arrows which indicate when the forces are in equilibrium. When the velocity is no longer changing, F net is equal to 0 and the magnitude of the drag force equals that of gravity. The terminal velocity of an object remains constant no matter what initial velocity it has, because its properties remain the same. The object's mass, gravity's acceleration, and the opposing drag force will always be the same regardless of initial velocity. Although it may take less time to reach terminal velocity when it travels at a faster initial velocity, the terminal velocity will still be the same. This concludes the presentation of Video Lab Report number 2.